Welcome to another video in a series on the xv6 operating system kernel. We finally have enough background to describe how new processes are created, and in this video you'll get to see how the fork system call works. Whenever one process wants to create another process, it invokes the fork system call. This is the only way that a new process can be created, with the exception of the creation of the initial process. The process that does the creating is called the parent process, and the newly created process is called the child process. The child process is a clone of the parent process. The child is almost exactly identical to its parent process. When some process, that's the parent, makes a fork system call, the kernel becomes active and creates a copy of the parent. Both processes are almost exactly identical. They have the same contents of their address spaces, the same register values, the same program counter, the same open files, and so on. Then, when the fork system call returns, the return happens in both processes. There is, however, a small but crucial difference. In the parent process, the fork system call returns the process ID of the newly created process. That's the child's ID. While in the child process, the fork system call returns 0. The code in both processes, the child and the parent, will typically take a look at the return value and use it to determine whether it's running in the child or the parent process. And the code can then take different actions depending on whether it needs to behave as a child or as a parent. If there's any difficulty, such as the kernel running out of memory and being unable to create the child process, the fork system call will return -1 in the parent. Let's begin with an overview of the fork system call. In summary, the system call will modify some kernel data structures, effectively creating a new process, and then it will return the process ID of the newly created process. Fork begins with a call to the allocproc function. Allocproc will search for an unused proc structure and will grab it and begin the initialization process. It starts by giving this proc structure a new process ID. Then it creates an empty address space and adds mappings for the trampoline and trap frame pages. Then, after the allocproc function returns, we copy the parent's virtual address space into this new address space. So, every code, data, stack, and heap page from the parent process is copied and added to the child's virtual address space. The permissions for each page in the child process will be set to exactly the same permissions that were on the corresponding page in the parent's virtual address space. We also initialize the remaining fields in the proc structure. We copy the size field, which is the number of bytes in the virtual address space, and since the virtual address space starts at 0, the size is just the same as the break address at the top of the heap. Next, we copy the registers and the program counter. When the fork system call was first invoked in the parent, the trap handler saved all the registers and the program counter in the parent's trap frame. Now, we copy the contents of the parent's trap frame into the child's trap frame. Copying these values means that when the child process gets a time slice and begins running in user mode, it will have exactly the same values in all its registers, and it'll begin executing at exactly the same spot, namely directly after the eCall instruction that invoked the fork system call. However, we also modify register A0 in the child's trap frame to set it to 0, so that the child process will see a returned value of 0 from the fork system call. Each process has a name, and we copy the name field, so the child process will be given the same name as the parent process. And each process also has a number of open files, and we copy all the file descriptors for the open files in the parent process into the child process, so that any file that was open in the parent process will also be open in the child process. And we also copy the current working directory, so that the child will be in the same directory. Then we set the parent pointer in the child's proc structure to point to the parent's proc structure. This is the only other difference between the child process and the parent process. they each have a different location in the parent-child hierarchy. This will come into play later when the child exits and we need to notify the parent process. So we make the new process a child of the parent by setting its parent pointer to point to the currently running process, that is, the process that's called fork. And finally, we set the state of the child to runnable. At this point, we're done creating the child process. It's now a normal, runnable process, and it will be given a time slice whenever the scheduler comes to it. After this, the system call is complete. It ends by returning the process ID of the process that just got created. Now let's look at the code. To handle this system call, the trap handler will invoke sysfork. Sysfork simply calls kfork to do the work. Whatever kfork returns, sysfork will return. You know, kfork is only called from this one place, and obviously do-nothing functions like this offer an opportunity for optimization, but this organization seems reasonable enough. Here's the kfork function, which is in the file proc.c. We begin by getting a pointer to the parent's proc structure, and then we call the alloc_proc function. If there are any problems, we return -1 and we're done. But otherwise, alloc_proc returns a pointer to the new proc structure, which we will call NP, that is, the new process. Let's take a detour and look at the alloc_proc function before continuing with kfork. The comment says it all. Look in the process table for an unused proc structure. If found, initialize it as required to begin running and return with the lock held. If problems, return null. So, it begins with a loop that goes through the proc array looking at each proc structure. And for each, it first acquires the lock so it can look at the state. If it's not unused, then we release the lock and move on to look at the next one. If none is found, we return null. But if an unused proc is found, we jump to this found label with a goto, and note that the lock will remain held. Here we call alloc_PID to set the process ID field. We also change the status to used. Next, we call kalloc to get a page, and we will use that page for the trap frame for this process. So we save a pointer to the physical page that will back up the trap frame. If anything goes wrong, we call freeproc, which will free any pages that got allocated, zero out all the fields, and change the state back to unused. Then we release the lock and return null. But assuming that we didn't run out of memory, we next call proc page table. I discussed proc page table when I talked about the virtual memory functions, but basically it creates a new page table with the trampoline and trap frame pages already installed, but with nothing else. If that fails, we again call proc free to free any and all pages associated with this process and change its state back to unused, and then we release the lock and return. Then we prepare the context field of this process. Remember that the context field in a proc structure holds the state of the process, the registers. The context will be used by switch when we go from the scheduler to this process. Keep in mind that the scheduler will switch into executing the kernel thread for this process, so these are kernel registers, not user registers. When the scheduler selects this process in order to give it a time slice, which will be its first ever time slice, the scheduler will blindly load the registers from whatever got saved in the proc's context field at the end of the last time slice. But, well, of course, there was no last time slice. Instead, we're initializing these fields here so that when switch is invoked by the scheduler, it will load the registers and we'll start executing. alloc_proc zeroes out all registers. Then it sets RA, that's the return address register, to the address of a function called forkret, which we'll look at later in this video. We also set the stack pointer to point to the kstack page. Actually, since stacks grow downward in RISC-V, we set it to the very top of the stack page by adding page size. Finally, alloc_proc returns a pointer to the now initialized proc structure. Now, back in kfork, if alloc_proc fails, we return immediately. A failure would be due to either a lack of memory or because no unused proc structure could be found. So we simply fail and return -1 to the user program. Otherwise, we now have np, now pointing to a new proc structure, and that process is locked. Next, we invoke uvm_copy to copy all the pages from the parent into the child's virtual address space. This will make copies of all code, data, stack, and heap pages. The arguments are a pointer to the parent's page table, a pointer to the page table for the new process, and the size of the address space, which indicates the number of pages that need to be copied. If there are any problems, we call freeproc. As I said, freeproc will zero out all fields, return everything to the free memory pool, and change the proc back to unused. Then we release the lock on that structure and return -1. But assuming everything is good, we keep going. Here we copy the size field. And here we copy the trap frame, which copies from the parent to the child all the user registers that were valid in user mode, as well as the program counter. When the child begins executing, the core will have exactly the same state as the parent, and because the program counter is also copied, it will resume execution at the same location. However, we clear register A0 to 0. The child process will begin by examining A0 to see what the return value from the fork system call was, and it will find 0. And from this, it will know that it is the child and not the parent, so it will take whatever actions a child should take. Next, we run through the open file array of the parent. For each file that's open, that is, for each entry that is non-null, we call filedup to make a duplicate of that and add it to the child's open file array. And here we're making a duplicate of the current working directory and copying that, so the child will have the same current working directory. What exactly is being copied here will make more sense later on in this video series after I talk about files and inodes. And here we're copying the parent's name field into the name field of the child. And here we grab the process ID of the child. We're going to be returning that at the end of this function in a second. Then we initialize the parent pointer of the child process to point to the parent's proc structure. Whenever the parent pointer is accessed, either read or modified, we must be holding a lock called wait lock. So we acquire that lock before and then release it after this modification. Finally, we set the state of this process to runnable, and then we return the process ID of the process we just created. Recall that we've been holding the processes lock, so we've got to release it before we return, and we do that here. And at this point, the child process has been created, and it will get scheduled whenever the scheduler gets around to it. But also notice that we release the parent's process lock here, and then reacquire that same lock here. What's going on with that? Why don't we just keep the lock while we update the parent pointer? Why release and then almost immediately reacquire this lock? Also notice that we don't just return the PID field. We first copy it into a local variable, and then we return that. This is because we need to retrieve the field when we're holding a lock on the process. It's possible that the minute we release the lock, this proc structure will get scheduled. It will run. It will exit. And another fork could be called, which will grab this process, and a new process ID could be assigned. Of course, this is highly unlikely, but this sequence of events could occur. And in an operating system, we have to assume that anything that can occur will occur. So if we just simply grab the PID from the proc structure after releasing the lock, we could in fact get the wrong number. So that's why we grab the process ID while we're still holding the lock. But we still haven't figured out why we are releasing this lock and then reacquiring it. This is done to avoid potential deadlock. Let's review deadlock. Here's a simple deadlock situation. We have two processes and two locks. This diagram indicates that lock A is currently held by process 1 using a solid arrow. And likewise, we see that lock B is currently held by process 2, again indicated with a solid arrow. Let's assume that process 1 wants to acquire lock B. That is, it's called the acquire function and is trying to obtain lock B, which is impossible because it's held by process 2. So the acquire function in process 1 will be spinning, waiting. Meanwhile, process 2 wants lock A, so it calls acquire, and it is also spinning, tied up in its acquire function, waiting on lock A. So this is deadlock. In general, a deadlock occurs whenever we have a cycle in a graph such as this, showing processes and locks. This is a simple cycle, but deadlock can also involve a larger cycle. Deadlock is a cyclic wait situation. Process 1 can't proceed because it can't get lock B. Process 2 can't proceed because it can't get lock A. They're both frozen, waiting on each other. Now, I haven't yet talked about the kexit function, but in order to see the potential deadlock problem, let me tell you what happens there. Kexit is used to terminate a process, and as part of that, it must take all the dying processes' child processes and move them to a new parent process. To do this, to modify parent pointers, it must first acquire a lock called waitLock. Then, as part of this reparenting, it must invoke the wakeup function to possibly awaken the new parent to let it know that it has created a new child in case it is asleep, waiting for that event. But remember that the wakeup function will momentarily acquire processes' locks as it tries to determine which processes need to be awoken. In summary, kexit first acquires waitLock, then acquires process locks. Now back in kfork, we're holding a process lock and we need to obtain a waitLock in order to set the child's parent pointer. So here's the situation we might have if we're not careful. kexit is holding waitLock and trying to acquire a process's lock. kfork is holding a process lock and trying to acquire waitLock. If we allow this, we now have the potential for deadlock, which we can't permit. To prevent deadlock in xv6, we impose an order on all locks and always make sure to acquire locks while respecting this order. In xv6, we must always acquire waitLock before any process lock. We are not allowed to acquire a process lock and then acquire waitLock. That's why we must temporarily release the process lock before we acquire waitLock in order to update the parent pointer. Now keep in mind that during this time, the state of the process is used, so nobody else will mess with this process. If the scheduler, or maybe some other thread running alloc proc, looks at this proc structure, it'll find that its state is used. It may temporarily lock it to look at the state, but it'll see that it's in use, and then it will quickly unlock it and move on to look for some other proc structure. Then, after we're done initializing the parent pointer, we can safely reacquire the process lock and then change its state to runnable and then release the process lock again. Now kfork is done and it can return to the user code in the parent process. Next, let's take a look at what happens in the child process. Its state was made runnable, so at some point the scheduler on some core will select it and give it a time slice. The scheduler does not see it as any different from any other runnable process, so it will do the same things as we discussed in previous videos on scheduling. Namely, it will grab its process lock, change its state to running, and invoke the switch function to perform a context switch into it. Switch will then load the registers from whatever was saved in the process's context, which normally would be the registers that were saved when the last time slice ended. However, for new processes like this, we've saved some special values for the RA and SP registers. Recall that when we set up the new process in alloc proc, we stored values directly into the process's context area. The RA field in the context, that's where the return address register is, was set to contain the address of a function called forkret. And the SP field in the context, that's where the stack pointer register would be saved, was set to point to the beginning of the kernel stack. The stacks go downward, so we stored the address at the top of this process's kstack page. Well, switch will first save the scheduler's registers, and then it will load the RA, the SP, and the S registers from the process's context area. We don't care about the S registers because this thread is essentially a new thread, but the RA and SP registers matter. The result is that when switch executes its return instruction, it will cause a jump to the forkret function with a fresh, fully empty stack page that's available for use. Now, normally functions are called, not jumped to, but a jump to this function is okay since it will not be returning. Instead, it'll do some things, ending with the sret instruction that transfers the core into user mode, and the first time slice will begin. From then on, there's nothing special about this, and the timer interrupts will work just as we've discussed in previous videos. In order to understand forkret, let's first review what happens in a normal trap. Here again is my roadmap diagram, which shows the handling of a trap. First, the uservec assembly code will save the user's registers in the trap frame, and then it will call usertrap. Let's imagine that we have a timer interrupt, so the trap handler will end the previous time slice and call the scheduler. Let's focus in particular on what happens when execution comes back to this process, and on what happens as we return to user mode. For the first time slice, we'll need to do something very similar to get into user mode for the first time. Essentially, we'll need to do this stuff down here, calling prepare return, and then getting back into uservec, which will restore the user's registers and execute the sret instruction. This diagram shows a detail of what normally happens when we come back from switch. Switch will normally return us to execution in sched, which restores int ina. Then it returns to yield, which releases the process's lock. Then we go back into usertrap and immediately call prepare return. After that, usertrap immediately returns to uservec, the assembly code function in the trampoline page. Note that usertrap returns a result in the A0 register, which will be the value to use for the SATP register. Back in uservec, we change into the user's virtual address space by updating the SATP register using what was returned in A0. Then uservec restores the registers and executes the sret instruction. Okay, so that's what forkret needs to do. To recap, forkret will need to release the process's lock, then it will need to call prepare return, then it will need to get back into uservec, the assembly code function. Previously, we returned from usertrap to uservec, returning the new SATP value in register A0. However, forkret will not return. It was never called, so a return is out of the question. What it will do instead is this. It will simply jump into uservec at the appropriate place, namely the label called userret, with register A0 containing the value to use for the SATP register. Instead of returning, it will use a call instruction to make that jump. And to get the new SATP value into A0, it will pass this value as an argument. Since RISC-V uses the same register, namely A0, for both returned values and for the first argument, this will work. Okay, now let's look at the code for forkret. First, we get a pointer to our proc structure. Then we release the process's lock, just as yield would have done. Now here's a subtle point. Recall that in sched, we restore the int ina field in our CPU structure, and we do that before we release the process lock. Forkret doesn't bother with the int ina field. In fact, it could be anything. So when we call release, that will call popoff, which will decrement inoff from 1 to 0, and restore interrupts to what they were before? Well, Popoff will consult int.ina and will either enable interrupts or leave them disabled as determined by int.ina. But since we haven't bothered to set int.ina, this could do either. So from here on, interrupts may or may not be enabled. So just keep that in mind. Next, we see this if statement. The idea here is that we want to execute these instructions on the very first time forkret is used. This variable, first, is defined up here and initialized to true. The static keyword, as you probably know, makes this a global variable, not a local variable. So there is only one copy shared by all invocations of forkret. The if statement asks, is this the first time we're doing this? If so, we do these statements, and we set first to false. So in the future, we will ignore all these statements. I don't want to go into detail at this time about what happens here. I'll come back to it later. But briefly, let me say that the way xv6 gets started is that it creates a single dummy process that doesn't actually have any code or even a virtual address space. When it gets scheduled for its first time slice, we'll do the stuff here. First, we perform some initialization for the file system. Then we invoke the kexec function, which is used to implement the exec system call. So it's as if this dummy process had called the exec system call itself, passing it the path name of an executable file. This string here names the program that will be executed. Okay, now let's ignore this first time initialization stuff and focus on getting this time slice started. So after this if statement, we call prepare return. What does prepare return do? Well, to see that, let's look at my roadmap diagram rather than at the code. It starts by disabling interrupts. That's necessary because they might have been enabled after we released the process lock. As a matter of fact, a timer interrupt could have happened sometime after releasing the lock before we get here, and this process might have had to wait for another time slice. But whether or not it did, we'll eventually keep executing this code. So anyway, in prepare return, interrupts are now disabled, so we can go straight through to the sret instruction without any interrupts. Then, as I discussed in an earlier video, prepare return does a few things in preparation for going back into user mode. It sets xv6, so any future trap in user mode will be handled by the uservec function in the trampoline page. It initializes several fields in the trap frame that will be needed when the next trap occurs. And this includes saving a pointer to the kernel's page table so we can switch back to it after the next trap. And we save the address of the user trap function so we can call it. And we save an initial value for the stack pointer. And we save the number of the core we're running on, since the TP register might get overwritten by the user code and we'll need to restore it after the next trap. We also set a couple of bits, namely the previous privilege bit and the previous interrupts enabled bit in the status register. The sret instruction will use these bits to change into user mode and to re-enable interrupts. And we load the sepc register with a saved copy of the program counter, which will also be used by the sret instruction. Okay, that's what prepare return will do. Then, back in forkret, the last instruction will jump into the assembly code in the trampoline page. This is a call statement which will do that jump. We use a call even though there will be no return to this code. And what address are we jumping to? We want to jump to the userret label in the trampoline code. Here we define and compute a 64-bit integer value named trampoline userret. Trampoline, in all caps, is the address of the trampoline page in high memory. And to that we add the offset from there to the userret label. Then, in the call instruction, we coerce that computed number into a pointer to a function that takes a single argument and returns void. And we pass, as an argument, this variable SATP, which we defined up here. This is a pointer to the root of the page table tree for the address space of this process. The make SATP macro will alter that address into the form that's needed when we store it into the SATP register. And remember that when we pass arguments, the first argument will be passed in register A0. So what these statements do is move that page table pointer into A0 and jump to the label userret in the trampoline page. Going back to the roadmap diagram, the userret label is right here. The assembly code will move the value in A0 into the SATP register, which switches the core from the kernel's virtual address space into the user's virtual address space. Then it restores the registers from the trap frame. Well, in a normal trap we can say restored, since these would have been saved at the beginning of the trap handler. But since we're starting a new process and this is its first time slice, these registers are not technically being restored. Well, I suppose they are being restored, but to what was saved when the parent originally made the fork system call, and they were saved as part of the system call trap in that process. But in any case, they're being loaded with values from the trap frame, which in this case will be their initial values. Finally, the assembly code executes the sret instruction. This switches the core into user mode and enables interrupts. And the first time slice for this process now begins. Since we're looking at the fork system call and we are now starting the child, when sret loads the program counter from SEPC, it'll be causing the first user mode instruction to be the instruction directly following the eCall instruction. So the child process will experience what looks exactly like a return from the fork system call, with the exception, of course, that register A0 has been modified to contain 0. So, isn't all of that cool? Once you understand it, it all makes sense, and it obviously works. Now, of course, I realize that when you first encounter all this, it may not be at all obvious. So, anyway, I hope my explanation of the fork system call has helped you to understand it. Okay, that's it for this video. Let me end by saying thanks for watching, and I'll see you in the next video. And, again, if you are in a class studying xv6, will you please share this playlist with other people who might benefit from it? Thank you.